Welcome friends to another session on differential geometry. We have completed our discussion on the intrinsic theory of surfaces in Riemannian geometry. Now we look at the properties of a surface as it lies in R3. Embedded manifolds in R3. Part 1. Let MF be a submanifold of R3 where M is an oriented 2 manifold. Let M be given the Riemannian structure induced from F. For V1 V2 element of T of M comma M, the inner product V1 V2 on M is equal to the inner product df V1 df V2 on Fm. Definition: given MF, the spherical map on M is the map S from M to S2 defined as follows. For M element of capital M, let S of M is an element of T of R3 F of M with the unit vector perpendicular to df of T mm, that is consistent with the orientations of T mm and T R3 Fm. That is, if V is a unit vector in T mm, then Sm is the unique unit vector in T R3 Fm such that dfv dfiv Sm is an oriented orthonormal basis for T R3 Fm. Identifying T R3 Fm with R3 in the usual way, we may regard S of M as a point in S2. See figure 1. We shall find it convenient to identify T of mm with df of T mm. Furthermore, since df T mm and T S2 Sm are the same subspace of R3 under the usual identification of the tangent spaces to R3 with R3, we shall identify T mm and T S2 Sm. Then ds of m from T mm to T of S2 Sm, which is equal to T mm. So ds of m is a linear transformation from T mm into itself. The main result of this chapter is the theorem of Gauss, which is the curvature k of m of capital M at small m is equal to the determinant of ds of m. In fact, Gauss originally defined k for embedded manifolds to be this determinant, and he was surprised to discover that k was in fact intrinsic. That is, k depends only on the Riemannian structure on capital M and not on the particular embedding f. Let us first note what manifolds in R3 look like in local coordinates in terms of the spherical map. For f from M to R3, let Fj is equal to Rj for j equal to 1, 2, 3, so that f of m is equal to f1m, f2m, f3m for all small m element of capital M. Here Rj are the coordinate functions on R3. Let mu from U to M be a smooth injective map from an open set U subset of R2 onto an open set in M such that mu inverse is smooth and such that if T is a 2 form on M which gives the orientation of M, then mu star tau is a positive multiple of dr1 with dr2. Thus, mu inverse is an oriented coordinate system on mu of U. Let xi equal to Ri composite mu inverse for I equal to 1 and 2 denote the coordinate functions on mu of U. Then dou by dou xi is equal to d mu dou by dou Ri and df dou by dou xi is equal to df composite mu dou by dou Ri is equal to summation k equal to 1 to 3 dou fk composite mu by dou Ri to dou by dou Rk for I equal to 1 and 2. So that the matrix for df relative to the basis set dou by dou xi for T mm and set dou by dou Rj for T R3 Fm is dou f, which is equivalent to the matrix dou f1 composite mu by dou R1, dou f1 composite mu by dou R2, dou f2 composite mu by dou R1, dou f2 composite mu by dou R2, dou f3 composite mu by dou R1, dou f3 composite mu by dou R2. The Riemannian structure on mu of U is then given by the inner product dou by dou psi I, dou by dou psi j is equal to summation k equal to 1 to 3 dou fk composite mu by dou Ri, dou fk composite mu by dou Rj for ij element of set 1, 2. Since df dou by dou x1 cross df dou by dou x2, that is the cross product in R3, is perpendicular to df T mm at each point small m element of capital U and is consistent with the orientation of T mm and T R3 Fm, the spherical map on mu u is given by S of m is equal to df dou by dou x1 cross df dou by dou x2 the whole divided by df dou by dou x1 cross df dou by dou x2, which is equal to 1 by a dou f1 composite mu by dou r1, dou f2 composite mu by dou r1, dou f3 composite mu by dou r1 cross dou f1 composite mu by dou r2, dou f2 composite mu by dou r2, dou f3 composite mu by dou r2, where A is the magnitude of this cross product. In particular, we see that S is a smooth map. Now consider a fixed point m0 element of capital M. Altering f by a translation and rotation if necessary, this will leave the induced Riemannian structure unchanged. We may assume that f of m0 is equal to 0 and that df t of m0 is tangent to the r1 r2 plane capital R2 and is oriented consistently with the natural orientation of R2, that is f star dr1 meet dr2 gives the orientation of t m0. You can see figure 2. Let small p from R3 to R2 be the projection, that is p of u1 u2 u3 is equal to u1 u2. Then p composite f from m to R2 such that p composite f of m0 is equal to 0 and dp composite f of m0 is equal to dp composite df of m0, which is equal to df of m0, maps t m0 isomorphically onto t R2 0. By the inverse function theorem, there exists a neighborhood u of 0 in R2 such that p composite f inverse is defined and is smooth on u. Let mu equal to p composite f inverse from u to m. Then mu inverse is a local coordinate system about m0. Moreover, since p composite f composite mu is equal to identity on u, f composite mu of u1 u2 is equal to u1 u2 g of u1 u2 for u1 u2 element of capital U, where g is equal to r3 composite f composite mu from u to r1. Thus, if x1 x2 are the coordinate functions on mu u, then the matrix df relative to this coordinate system is 1 0 0 1 dou g by dou r1 dou g by dou r2, and the spherical map on mu of u is given by S of mu u1 u2 is equal to 1 by a u1 u2 into 1 0 dou g by dou r1 u1 u2 cross 0 1 dou g by dou r2 u1 u2, which is equal to 1 by a u1 u2 into minus dou g by dou r1 u1 u2 comma minus dou g by dou r2 u1 u2 comma 1, that is S composite mu is equal to 1 by a into minus dou g by dou r1 minus dou g by dou r2 1, where a is equal to the square root of dou g by dou r1 the whole square plus dou g by dou r2 the whole square plus 1. Note that at m0 equal to mu of 0, Sm0 is perpendicular to df t mm0, which is equal to r2. Implies that dou g by dou r1 at 0 is equal to dou g by dou r2 at 0 is equal to 0 and a of 0 is equal to 1. Now, under our identification of t of mm0 with df t mm0, dou by dou xi of m0 becomes identified with dou by dou ri at 0 for I equal to 1 and 2. So that the entries bij for the matrix for ds from t mm0 to t mm0 relative to the basis set dou by dou xi are given by bji is the inner product ds dou by dou xi dou by dou xj at m0 is equal to the inner product ds composite mu dou by dou ri dou by dou rj at 0, which is equal to drj ds composite mu dou by dou ri at 0, which is equal to drj composite s composite mu dou by dou ri at 0, which is equal to dou by dou ri rj composite s composite mu at 0. Thus, B11 is equal to dou by dou r1 into minus 1 by a dou g by dou r1 at 0, which is equal to 1 by a square dou g by dou r1 dou g by dou r1 at 0 minus 1 by a dou square g by dou r1 square at 0, which is equal to minus dou square g by dou r1 square at 0. And similarly, B12 is equal to minus dou square g by dou r1 dou r2 at 0, which is equal to B21, which is equal to dou square g by dou r2 square at 0. That is, ds m naught, the matrix is given by minus dou square g by dou r1 dou r1 minus dou square g by dou r2 dou r1 minus dou square g by dou r1 dou r2 minus dou square g by dou r2 dou r2 at 0. In particular, assuming Gauss theorem, which still remains to be proved, that k is the determinant of ds, we obtain a qualitative description of the behavior of f of capital M near the point f of m naught under various assumptions on the curvature k m naught. For from the critical point theory of function of two variables, we know that the function g will have a maximum at the critical point 0 provided that the eigenvalues of the matrix dou square g by dou r1 square, dou square g by dou r1 dou r2, dou square g by dou r1 dou r2, dou square g by dou r2 square at 0 are both negative, and that g will have a minimum if the eigenvalues are both positive. Thus, if k of m naught is greater than 0, then near 0 f of m lies either completely above or completely below the R2 plane. On the other hand, if k of m naught is less than 0, then ds of m naught has one positive and one negative eigenvalue, and g has a saddle point at 0. If k of m naught is equal to 0, the behavior of f of m near 0 is undetermined. See figure 3. Local geometry of embedded manifolds. In order to prove Gauss theorem, we need an explicit description of the local geometry of embedded manifolds. Theorem 1. Let MF be an oriented 2 manifold in R3. Let E1, E2 from S of M to R3 be defined by E1 of MV is equal to df of V and E2 of MV is equal to df of IV. Let psi be the one form on S of M defined by psi is equal to the inner product dE1 E2, that is for MV element of S of M and T element of T SM MV, dE1 T is an element of T R3 E1 MV which is equal to R3. Psi of T is equal to the inner product dE1 of T E2 MV, then psi is the one form of the Riemannian connection on M. Proof. Let us prove the invariance first. For G is equal to e raised to I theta element of S1, G star psi is equal to psi composite dG which is equal to the inner product dE1 composite dG comma E2 composite G which is equal to inner product d of E1 composite G E2 composite G. But for MV element of S of M, E1 composite G of MV is equal to E1 of M comma cos theta V plus sin theta IV which is equal to cos theta df V plus sin theta df IV, and E2 composite G at MV is equal to E2 M comma cos theta V plus sin theta IV which is equal to minus sin theta df V plus cos theta df IV. So, E1 composite G is equal to cos theta E1 plus sin theta E2, and E2 composite G is equal to minus sin theta E1 plus cos theta E2. Thus, d of E1 composite G is equal to cos theta dE1 plus sin theta dE2. Now, since the inner product E1 is equal to 1 comma inner product E2 which is identically equal to 1, and inner product E1 is identically equal to 0. We have 0 equal to d of inner product E1 which is equal to 2 times inner product dE1 and 0 equal to d inner product E2 which is equal to 2 times inner product dE2 0 is equal to d inner product E1 which is equal to dE1 plus E1 dE2. So that inner product dE1 is equal to inner product dE2 is equal to 0, and inner product E1 dE2 is equal to minus inner product dE1 Hence, G star psi is equal to inner product d of E1 composite G E2 composite G which is equal to cos square theta plus sin square theta inner product dE1 which is in turn equal to psi. Next, we will see normalization. For MV element of S of M, V of MV is equal to gamma dot 0, where gamma from R to Sm is given by gamma of theta is equal to M comma cos theta V plus sin theta IV. Hence, psi of V of MV is equal to psi of gamma dot 0 which is equal to the inner product dE1 gamma dot 0 E2 gamma dot 0 which is equal to inner product E1 composite dot gamma at 0 df of IV. But even composite gamma of theta is equal to cos theta dfv plus sin theta df of IV. So that even composite dot gamma of 0 is equal to minus sin theta dfv plus cos theta df IV at 0, which is equal to df of IV, and psi of v of mv is equal to 1. Thus, psi is a connection form on M. To verify that it is the form of the Riemannian connection, it suffices to check that the simplified forms of the first structural equations are satisfied. To do this, note that when mv is an element of S of M and t is an element of T of Sm mv, omega 1 of t is equal to inner product d pi of t comma v, which is equal to inner product df composite d pi t dfv, which is equal to inner product d of f composite v of t E1 of mv. So, omega 1 is equal to inner product d of f composite pi E1, and similarly omega 2 is equal to inner product d of f composite pi comma E2. Also note that the component of d f composite pi in each rj direction is the exterior differential of a function, namely inner product d f composite pi dou by dou rj is equal to d rj composite d f composite pi, which is equal to d of rj composite f composite pi. So that d of d f composite pi is equal to 0, where the exterior derivative of a 3-tuple of forms is computed component wise. Hence, d omega I is equal to d of inner product d f composite pi comma ei, which is equal to inner product d of d f composite pi ei minus d of f composite pi dei. D omega I is equal to minus inner product d of f composite pi comma dei. But d of f composite pi is equal to inner product d of f composite pi comma E1 into E1 plus inner product d f composite pi E2 into E2. Since E1 of mv and E2 of mv form an orthonormal basis for df of t mm for each mv element of S of M. Thus, d of f composite pi is equal to omega 1 E1 plus omega 2 E2. Hence, from the previous equation, d omega 1 is equal to minus inner product omega 1 E1 plus omega 2 E2 comma d E1, which is equal to minus omega 2 meet inner product E2 comma d E1, which is equal to minus omega 2 meet psi, which is equal to psi meet omega 2, and d omega 2 is equal to minus inner product omega 1 E1 plus omega 2 E2 comma d E2, which is equal to minus omega 1 meet inner product E1 comma d E2, which is equal to omega 1 meet psi, which is equal to minus psi meet omega 1. Interpretation of parallel translation for embedded manifolds. Let alpha be a curve in M and alpha tilde some lift to S of M. Then E1 composite alpha tilde is a curve in R2 lying on the unit sphere, so that d of E1 composite alpha tilde into d by dt at t0 is equal to d by dt E1 composite alpha tilde at t0 is always perpendicular to E1 composite alpha tilde of t0. Now, alpha tilde is horizontal if and only if psi of alpha tilde is equal to 0. By theorem 1, this is the case if and only if d of E1 composite alpha tilde d by dt at t0 is perpendicular to E2 composite alpha tilde dot t0. Since E1 and E2 span the tangent space, alpha tilde is horizontal if and only if d by dt E1 composite alpha tilde at t0 is perpendicular to df tm alpha t0 for all t0. Thus, if x is a unit vector field defined along alpha and alpha tilde of t is equal to alpha of t comma x of alpha t, then x is parallel along alpha if and only if alpha tilde is horizontal. If and only if d by dt E1 composite alpha tilde is equal to d by dt x composite alpha is always perpendicular to the manifold. That is, x is parallel along alpha if and only if x composite alpha is constant along the manifold, such that the tangential component of the derivative of x composite alpha in R3 is identically 0. For embedded manifolds, this characterization can be used in place of the abstract notion of connection. Now, we will move on to theorem 2, which is the Gauss theorem. Let MF be an oriented 2 manifold in R3. Let S from M to S2 be the spherical map. Then for each M element of capital M, determinant of ds of m is equal to k of m. Proof. Let S tilde from Sm to S of S2 be defined by S tilde of mv is equal to S of m df of v. Let omega 1, omega 2 and psi be the structural one forms on Sm, and let omega 1 bar, omega 2 bar and psi bar be the corresponding forms on S of S2. Then S tilde star psi bar is equal to psi. For S tilde star psi bar is equal to psi bar composite d S tilde, which is equal to inner product d E1 bar composite d S tilde E2 bar composite S tilde, which is equal to inner product d of E1 bar composite S tilde E2 bar composite S tilde. But E1 bar composite S tilde of mv is equal to E1 bar S of m df of v, which is equal to df of v is equal to E1 of mv. E2 bar composite S tilde of mv is equal to E2 bar Sm comma dfv, which is equal to I dfv, which is equal to Sm cross dfv, which is equal to df of iv, which is equal to E2 of mv. So that Ei bar composite S tilde is equal to Ei and S tilde star psi bar is equal to inner product d E1 E2, which is equal to psi. S tilde star omega 1 is equal to A11 omega 1 plus A12 omega 2, and S tilde star omega 2 is equal to A21 omega 1 plus A22 omega 2. These are equation 2, where the Aij are the smooth functions on Sm such that the matrix A11, A12, A21, A22 at mv is the matrix for dsm relative to the basis set v, iv for t of m, m. For if mv is an element of Sm and t is an element of t of Sm mv, then S tilde star omega 1 bar of t is equal to omega 1 bar composite ds tilde of t, which is equal to inner product d pi bar ds tilde t comma df of v, since S tilde of mv is equal to Sm comma dfv, which is equal to inner product d of pi bar composite S tilde of t dfv, which is equal to inner product ds composite pi t df of v, which is equal to the inner product ds d pi t comma df of v, which is equal to the inner product ds omega 1 t v plus omega 2 t iv comma dfv, which is equal to the inner product dsv comma v omega 1 t plus inner product ds iv comma v omega 2 t, since dfv is identified with v. Similarly, S tilde star omega 2 bar of t is equal to inner product dsv comma iv omega 1 t plus inner product ds iv comma iv omega 2 t, thus completing the proof for statement 2. Third one, for each m element of m, determinant of dsm is equal to k of m. For minus k omega 1 meet omega 2 is equal to d psi, which is equal to d of S tilde star psi bar, which is equal to S tilde star d psi bar. The 0 is equal to S tilde star minus omega 1 bar meet omega 2 bar, since S2 has constant curvature, which is equal to minus S tilde star omega 1 bar meet S tilde star omega 2 bar, which is equal to minus of A11 omega 1 plus A12 omega 2 meet A21 omega 1 plus A22 omega 2, which is equal to minus of A11 A22 minus A12 A21 omega 1 meet omega 2. So that k is equal to the determinant of the matrix A11 A12 A21 A22, which is equal to the determinant of dsm. Note that the linear transformation ds of m is called the second fundamental form of capital M at small m. It is a self-adjoint linear transformation, since its matrix relative to the special coordinates discussed previously is the symmetric matrix minus dou square g by dou r1 square minus dou square g by dou r2 dou r1 minus dou square g by dou r1 dou r2 minus dou square g by dou r2 square. We will see some more theorems which says geometrically how parallel translation behaves for submanifolds in R3 in the next session. Before we conclude, let us summarize what we have learned in this session. We defined a spherical map and have seen what manifolds in R3 look like in local coordinates in terms of the spherical map. The main result of this chapter is the theorem of Gauss, which says that the curvature k of m of capital M at small m is equal to the determinant of dsm. We have seen K depends only on the Riemannian structure on capital M and not on the particular embedding F. Here are some problems for you to try out. First one, the map F from R1 to R2 given by f of t is equal to t square t cube is proper and injective but is not an embedding. Its differential at x equal to t is not injective. Prove this statement. Second one, find an example of a two-dimensional embedded submanifold of R3 that is not a level set of a single function. Now let us see some books for further reading. First one, Introduction to Differential Geometry by J. A. Thorpe, Springer Verlag. Second one, Lecture Notes on Elementary Topology and Geometry by I. M. Singer and J. A. Thorpe, Springer Verlag 1967. Elementary Differential Geometry by B. O. Neal, Academic Press 1966. Fourth one, Lectures on Differential Geometry by S. Sternberg, Prentice Hall 1964. Fifth one, Differential and Riemannian Geometry by D. Lovitz, Academic Press 1965. Sixth one, Riemannian Geometry by S. Gallert, D. Hallin and J. Lafontaine, Springer Verlag 1987. And seventh one, Riemannian Geometry and Geometric Analysis 4th edition by Jürgen Jost, Springer Verlag. Thank you for watching this session. We will continue with this topic in the next session. Till then, goodbye.